Hey, what's up, guys? This is Chung here. So today, let's take a look at this number 974 subarray sums divisible by k. So basically, you're given like array a of integers, and you need to return like the subarray, right? Which means the contiguous, non-empty arrays that have a sum which divisible by k, right? So for example, we have this array A here, and the k is 5. So we have 7 subarrays in totals, which is divisible by 5, right? So this one, this one, this one, this one. Yeah, so remember 0 is also divisible by k because, right? So 0 divided by k is also equals to 0. That's why 0 is also like a another a value, right? Uh, so here's the constraints, right? So the length of the 30,000, right? So for this kind of problem, every time when you see like this contiguous like subarrays, it's very common to use prefix solutions for it. So let's see how can we solve this kind of problem. And assuming we have a running sum, right? So because it's very, like I said, it's very common to maintain a running sum, right? At the current location. Let's say we have the current running sum equals to x, right? And then let's say we have some numbers here, right? Before this current number here. Let's say we have O here, right? So let's say the current running sum for this one is x. So how can we know if for at the current locations, let's say if there's any subarray, right, that can basically that a subarray end with the current number. Okay. So how can we calculate that? I mean, the brute force way is that we loop through all the presums, right? All the presum in the previous location, right? And then if there's a location, basically if we have x, and let's say for this kind of the previously presum is so this is sum 1, right? Let's say this is sum 1 here. So basically we need to loop through all the previous presums, right? And then we need to know, let's say we have a sum 2 here. We want to check if the sum 1 minus sum 2 can be divided by k, right? So if it can, then we know, okay, we have find like a valid subarray, right? But as you guys can see, so this is like a O of n squared time complexity. Even though we're using like this kind of presum, we're maintaining like this kind of presum, right, in the hash table. But still, we have to loop through all of the previously presums to get the subarrays that, right, ending with a current number. So how can we do it? How can we do it in a more performant way, right? So let's try to draw some like numbers here. Let's say we have some presums, right? Let's say we have presum 2, and then we have some presum like let's say we have 17, right? And then we have presum 26, and then we have presum 35. So as you guys can see here, right? I mean, let's say, oh, and also assuming the k is equal to 3 in this case. Okay, so when we are at the presum 2 here, right? So this is the presum. So obviously 2 cannot be divided by 3, right? So that's why we skip that. And then, but when we add the presum 17 here, you know, as you guys can see, we have like a difference, right? So basically 17 minus 2 equals to 15, right? So we have a, between the 2 and the 17, we have a 15 here. So the 15 is divisible by 3, right? So this is one of the subarray, right? That can be divisible, is divisible by this k here. Now later on we have another like pre-sum, like which is 26, right? So between 17 to 26, this is what? This is 9, right? So okay, 9 is also another one, right? Similarly for this one, it's also a 9, right? So 9 is also another like prefix sum. But when we are at 26 here, so how many more subarrays we have find out here? Not only these two here, right? We also find basically we find this 9 here, and we also find another one, basically another subarray between 2 and 16, which is 24. So this one is also another subarray, can be is divisible by 3, right? Similarly at 9 here, so by having 35 as a new prefix here, we have basically this is going to be 1 plus 2 plus 3, right? Because by having 26 here, we find 2 more subarrays, and when we're at 35 here, actually we're finding 3 more. Basically, this is the first one, and then from 17 to 35, this is the second one, right? This is like the basically here's the 18, and then from 2 to 35, this is the third one. That's the 33, right? So then what's in common? So what are the common thing with those 4 prefix, right? So if we do a prefix sum, right, divided do a modular with k here, they are all end up with the same number, which is 2, right? So 2 do a modular with k has 2, same thing for 17, 26, and 35. And then it leads us to to another solution. Basically, we can just use like a hash table or dictionary to store the key, basically to store the the, the values for each presum to after modular by k, right? And then every time when we have like a new key here, basically we increase that count of that dictionary, right? Basically at the beginning, that count is 1, right? Let's say we have dictionary, right? And the key is 2, right? And the value at the beginning, it will be 0. So when we add 2 here, we don't add anything. But after processing 2 here, that value becomes 1, right? And then when we're at 17 here, basically the new answer will basically do an answer to a plus of this dictionary of key here, of key. So when we're at 17 here, right? So this basically we're increasing 1, and after that we also increase this dictionary of the key by 1, right? We do this one, do a plus 1, so that when we're at 26 here, this one becomes to 2, right? So that's why we can add 2. Same thing for the 35, we add 3. Yeah, so basically the idea here. So we just use the dictionary to maintain the frequencies. The frequency, basically how many times this key has appeared, and then that's going to be the values we're going to use to accumulate to the final result, right? Oh, and one more thing. So when we define these hash tables, there's like edge cases, which means that the 0, right? So let's say the k is 3, and what if the first number is 3? The first number is 3. So in this case, right, 3 modular by do a modular with 3, we have 0, right? But 3 itself, in this case, is also like an array here, right? So which means that when we create these dictionaries here, we need to initialize this 0 and 1, in this dictionary. So which means that, at the beginning, we assume that, with zero as a key, it appears once, so that we can handle this corner case here. Yeah, I think enough talk. So actually, after figuring out the pattern here, the code is pretty simple here. So we have running sum, and then we have answer equals 0, right? Then, like I said, we have DP. I'm using a DP here, so I initialize from 0 with 0 key is 0 and the count is 1. So for num in A, right? So first we have running sum updated, and then we have the key, right? So the key will be the running sum divided by k, and then if key in the dictionary, right, we accumulate this answer by with the frequency of the current key, right? And after that, it will dp k we increase by 1. Else, right, if the key is not in this dp, we simply insert this one, right? Insert the key with 1. Yep, and then in the end we simply return the answer. Yep, I think that's it. So run the code, click accept it, right, and then submit. Yep. So for this one, as you guys can see, the time complexity is obviously O of n, right? Because we only have a single for loop here, and to maintain this dictionary, it's just like the O1 time, right? Both the insert and update is O1. And space complexity, of course, is also O of n, because we need to maintain basically the key for each of the well, actually no, actually the space complexity is not O of n, it's O of k in this case, because we do a modular, right, with the k here, so the key is bounded with how big the k is. Yeah. So this is the time complexity, right? This is space time complexity here. Yep, I think that's pretty much I want to talk about for this problem, and I'll just stop here. Thank you for watching this video, guys. Stay tuned. See you guys soon. Bye bye.